Just 1 minute, I'll start the recording. Yes. So in the last class, before the discussion of assignments, we were talking about object-oriented programming. So if we go back where we had discussed about getters and setters, and then we moved on to see what are properties. So there was a little bit confusion on properties, and then we discussed class methods, and I will take this section also in today's class. All right. So yes. So before moving into that, what we have here, you see, this is actually a definition of an object type called student. And inside this object type, we have the init method, which verifies if the name is not empty and raises an error. And over here, this it checks if the I have I done. Okay, just let me delete these parts from here. Let me come over here and discuss. Yes. So it was checking that if the name is empty or not. And if it was empty, then it was raising an error. And if the student is in some section or not. So first, it will check that it should be in A, B, C, or D. And if not, then we should raise an error. And it was a value error called invalid section. It had an attribute called name in which the name was stored, and an attribute called section in which section was stored. All right. Then we had a underscore underscore str underscore underscore method to print. So if we call this instance of this object from any print statement, then you will get this f string as the output. Then we saw that it is better to call the object's instance and get the attribute using functions, getters and setters. In that case, it will not modify or make some changes in the attributes. That is why we had getters and setters. So these are functions which we have defined. All right. And in setter, when we were setting name, we had to check again. OK, this is set section, not set name. So if we had a setter called set name, in that also we had to check if the name is empty or not. But this is set section. So this is checking if the section exists or not. All right. Then we had a main function which get. So which calls this function get student. All right. And it sets the section of the student using the set section function. All right. And you see when you say get student, just 1 minute. OK, here is it. Here is the function. That is why I was getting confused. So this is the function called get student. And in this get student, the instance of the object is created. You see, we take the input name from the user and a section from the user, and it returns an instance of that type. All right. So this is student type, and it passes the value name and section to the object type. Then it sets the section to A. So whatever the section the user has input, it updates it and it sets to A. Then it prints get name, get section, and it prints S. That means we'll get this str. This is called. All right. So this is what getters and setters is. So I don't have the context of how the flow was. That's why a little bit confusion. All right. So first I'll call this, and as usual, it will ask for the name. So over here, input name. So I'll say Arjun, and I'll set section D. All right. So it says section is D, but we have set the section as A. Therefore, this print says A Arjun is in section A. All right. So we know what a getter and a setter functions are. Now, there is another way to define getters and setters in Python, and that uses property of the object. So this property is actually a decorator. And what is a decorator? Decorator is actually a function which modifies other functions. So we'll not get into the details of what decorators are, but property is a one such decorator. All right. So whenever you say @property, what it does is, so we had attributes to this object. The first attribute was name, and the second attribute was section. So properties are special attributes. Those are also attributes of the object, but those are special attributes. So what we are saying is, and we define this as functions. All right, special attributes or these properties are defined as functions. Why? Because in that case, we can call it outside the for each instance of that object. This is not why, but this is what it is. All right. So we say def. So this will be the name of the property which you want to define, section, and this takes self, and it returned self dot underscore section. So actually, why have we done underscore section? You see, when you call s dot section, before that, you see this underscore before any variable in Python makes the variable private variable. All right. Uh, Private, there are three types of variables. Let me check. Public, private, and one more I forgot. You can help me, ma'am. There are three types of variables: public, private, and one more variables are there. I don't remember. These are in other languages as well. So public, private, and protected. Yes. So this is actually, so when you give one underscore, it is a private variable, and when you give two underscores, then those are protected variables. So this private variable is private to this uh, definition of the type. All right. And it is different from this section. So this is a property, and this is the variable or the original attribute. So in this definition, this was the original attribute dot. So not dot, section. So section was the original attribute. Over here, we are just overshadowing the section, and we are saying underscore section is the original attribute to the object, but we will call it by just section. So that is why the name is same, but an underscore is given to distinguish. So this is a property, and this is the original attribute which we have been using before this code. All right. Now, whenever you say self dot section or s dot section, where s is the instance of this student object, you are not actually calling this underscore section. You are actually calling this section. All right. Over here also, when you are saying self dot section, you are not calling self dot underscore section. You are actually calling this def section, this. All right. So this is actually a getter, and to make a setter, you have to say this is a way how it is defined. So when you define the property, the setter is defined as @ name of the property dot setter. So this is how a setter is defined. All right. And then the name will be same because this is the getter and this is the setter. Self will be passed. And since this is a setter, it will take one more uh, parameter. Over here it is section, and this is just the check if the section is exist or not. And here we are setting the original attribute underscore section to whatever the user has passed. All right. So this is actually the setting of value to the attribute. So whenever you say self dot section, you are not setting, you are just calling this setter function. And this function is actually doing the um, assignment, you can say. Yeah. So over here also, when you are saying s dot section, this is called, because it is an assignment equal to something. So this is called, this is checked, and then this assignment is done. And because of this, you see, we are not checking here if section not in ABC. Why? Because when you are saying self dot section, the control is coming over here and it is checking if section not in ABC, then raise the value error. So there is no point of checking here again. because this setter will automatically be called. This setter function will automatically be called. So this is what it is. All right. Any questions in this property? Hello. If you are, if you forgot the discussions in lecture 13, then it will be difficult to follow this part. Are you there, or are you able to understand?
I am here, sir. But I almost mean half of the discussions I forgot. Again, anyway, I'll read it again. I have to
All
run
right.
through this recording and I'll get this.
Yes, yes. So if you don't remember about this object discussion which we had, then it will be difficult for you to follow. All right. So class methods. So this class method is also something related to a type. Now, why do we need class method? You see, all the functions which we have defined over here. So these are just getters and setters, but there can be other functions also. Um, have we defined other functions? Over here, we have not defined other functions, but there can be other functions also inside the object. So you can make a calculator object, and inside that object, inside that definition of the object type, you can have multiplication function, division function, and all those things. All right. So why do we need class methods? So there is a way to define methods in an object, but why do we need class methods? You see, all the functions which we have defined so far are actually related to instances of objects. So what is an instance? If you forgot, I'll tell you. Whenever you say this student, so the student is the object type, and give the parameters it requires, it creates an instance of this type. All right, it creates an instance of this type. And we were storing this instance over here, we are storing it in S. All right, so this is one object of the type student. So S is an object of type student. In other words, you can say S is an instance of the object type student. All right, so this is one instance of the object type student, or this is one object of the object type student. So this is a type. This is the object. So this is one object of type student. You can have multiple objects of the same type. Like when you define strings, so you are having multiple strings. So those are instances of str object. All right. Now, so all these functions which we were defining, those were on instances. So when we were saying s dot section, so this is on the instance. So it is related to the instance, and that is why it takes self. You see, all the functions we had defined takes self because it is defined on instances of that type. But there can be cases where you don't. So where the function is not related to the instance, it is related to the class as a whole. So what example we are having here? We are saying that there are students and students have some section. So they're in a class and the class has section A, section B, section C, and section D. All right. So the example which I gave is, suppose there is a principal and that principal sets the section. So whenever a student comes to the admission, so take admission, the principal sets the section of the student. Now you see this function, or when I say principal, this is not, so when you can also say student, it doesn't matter. I'm saying this function assignment of student is not dependent on the instance of the student. It is actually a function of the class. So here the class is principal. So I'm defining an object called principal, and I'm saying this object will assign sections to a student. And this assignment function or method, you can say, because it is related to an object, this assignment is not dependent on instances. Whatever the instance, this function is applied. It doesn't require an instance. Without an instance, this function is there. It exists in the object. All right. So in that case, you have to say @class method. All right. So this principle exists, and whenever a student comes to it, it assigns a section. It is not an attribute of the student. So it is not related to individual students. So I'm not saying there is one principle for each student and that principle is for that student and there is one more principle for one more student. So it is not that. Principle is only one for all the students. It is not instance dependent. So each student doesn't have a principle. All right, is it clear?
Yes, sir.
Now this function, so since there is no instance, so I have to define something on which the function will be applied. Therefore, we have to say class. So CLS is actually class and whatever parameter it takes. Now I am saying name. So whatever is the input from the user is in section and I'm doing random dot choice, and this is how we are doing it. CLS dot SEC. And what is this SEC? SEC is a class variable. This section SEC, not section, SEC is a class variable. It is not defined inside any function. It is defined inside the class, and that is why it is a class variable. And this is the call to that variable. So CLS will refer to principal because it is inside principal, and it will say principal dot SEC. And therefore, inside this, we will have the list, this list, and random dot choice will pick any one from this list and we'll get the section. All right. So you see, when we run this, it is saying Arjun is in section A. And when we call principal dot assignment, we don't pass the class name. This is how we do. So whenever we had some call to a function, so over here you see student name comma section. So we are not, so the first um, parameter is, we don't pass the first parameter. So over here also we are just saying Arjun. So this is referring to the name, and then name is being written over here and it prints what section is in Arjun is in which section. And you can access the class variable just like you access the attributes of the instances by saying principal dot sec, and you will get the class variable value. All right, so this is what class method is. Now you may ask, give me one example of this, a proper example. So you see we had a student class. We had a student class. If you go back, we had a student class. All right, and we had a class which is not dependent on the, so we had a function get student which is not inside the student class. But if you think about it, get student is something related to student. So it is actually getting a student from the user. And it is better if we define this function which gets a student from the user inside the class itself. So whenever we say get student, so this is related to the student and it should be actually inside the student. And now you see this function get student is not dependent on the instance. It is actually creating an instance. So it is a class method. You see, this get student is a function which should be inside the object type called student. And there is no instance required for this because it is actually creating an instance. So it is a class method. All right. And you can put it inside the student class by saying @class method, and you can say def underscore. So I'm saying get def get. So I've not written get student. It is actually that only get student, and otherwise everything inside the function is same. And inside the main, when I say student dot get, this is how we call a class method. This will go here. The control will come over here. It will take some input, this input and this input. It will create the instance and then return it over here and it will be stored in S, and then print S will come over here and print whatever it is. So I hope this class method, which was not clear previously, is clear now. Any doubt? Any doubt?
No, sir.
All right. So Kalyavani ma'am, are you here? Ma'am? All right. So yeah, we'll discuss inheritance. So when we were discussing object-oriented programming in our first class, so if I come here and I can go in lecture 12. So when we come here, you will remember that um, we said that whenever we define an object, you can say it is inheriting from object, or you can just remove this and it will work, right? And we said that this is inheriting all the attributes, all the functions of object. So whenever you define object inside and in the class definition like this and say object, so whatever the attributes of objects are and whatever the functions of objects are all inherited by this type called fraction. And this is how inheritance works. What it means? It means that whatever is the property of this object, it will be passed on to this object. So for example, over here, we were saying that we have student and we can say what we can say. So I should give a better example. So suppose in this discussion of class 12, we were saying that there can be a function called animals, and there can be different kinds of animals like um, humans, cats, dogs, etc. And these animals have some types. So those have red blood cells, those can walk, and so on and so forth. And all these subclasses, humans, cats, dogs, will inherit all the properties and all the attributes because those are animals. Those are inside the animal class. So you can say, so if this is humans, you can just say bracket, and then you can say inherit all the property from animals. All right. I guess I have an example for students as well. Just give me 1 minute, I'll check. All right, so we can say, so let me do some things. So I can say class humans, all right, and it will inherit from object. Object is the most basic type in Python. It has attributes like plus, minus, subtracts, and so on. All right, it is the most basic object type in Python. We'll have a init method. So yeah, so Danish, I guess it will be difficult for you to follow, and that's all right because you have not attended previous classes.
Yes,
Yes,
sir. But I'm trying to understand all the things, and first I try to just listen all the lecture. But I'm just listening. Okay, what will be
no
happening in
problem.
this?
No problem. I just wanted to address you once. Kindly unmute yourself. Mute yourself. Yeah, thank you. So you see, I'm saying there is a class called humans, and this student is actually a subclass of humans, and it will inherit all the properties of humans. So I'm defining a class called human, and I'll say init. So what was init? Init was actually an initialization method which actually runs first when you create an instance of an object. All right. So I'll say def init and I'll say self, and suppose what attributes human can have. I'll say humans have names. So I'll say name. All right. And okay, just let me have only one attribute for now. And we can say an error. So error checking can be there. It is not required, but still I'm saying if not name, raise value error. You can just give any message. I can say missing name. All right. And now I'll assign the attributes. I'll say self dot name equal to name. So this is the name of the attribute, and this is the argument which we are passing, name. So it can have just n also for clarity maybe. All right. So this is the attribute, and this is the attribute, and this is the variable. All right. And there may be other functions also. For now I'll just say pass. There can be other functions. Now what I will do is I will say there is an object type called students, and it inherits the property of humans. I can say class students, and okay, just student, and I'll just write human. Therefore, this will indicate whatever is inside this object inherit everything. Now you see it has an init method. All right. So you may or may not write an init method. All right. Because if you don't have an init method, suppose init method is not there and you are saying just pass. So what it will do is first the control will come over here and check if this object has an init method or not. If not, then the control will come over here and it will see yes, it has an init method and it will do whatever this init method is asking it to do. So suppose I am saying s is equals to student and I'll just pass a name, Arjun, and you see although this class doesn't have a init method, but it will work because it will come over here and check if init method is there or not. If not, then it will go to the, you can say, parent class, or in technical terms it is called super class, and it will check if that method is there or not, and it will do the assignment. You see, name is not defined. Okay, it will be n. You see it is done, and when you do so, I have not defined a str method. So if I say def underscore underscore str underscore underscore self, and I'll just copy from above. Now you can just print to see if this has been created or not. You see, okay, I have not run this. Student has no attribute section. All right, so I'll just remove this. You see, Arjun is in, so we can run. All right, we have not defined an attribute called section, but now we will. Now what we'll do is, you see, humans may not have a section. What does it mean for a human to have section? But student can have section. So this class student requires an init method. So you will say def underscore underscore init underscore underscore. And whenever you define a function which is both here and here, so it can be any method. It is not just init method. Whenever you define a function which is both inside the child class and parent class, the control will run that function on which it is called. So you see the object is actually of the type student. So it will run the function inside the student and it will not go above. So it will not go above. It has run here and then it will just leave it. It will not go above. All right. So this is called. So this is how. So initially it was inheriting from the above class, but now you're overwriting it. All right. This is just overwriting of the properties, functions, attributes, and so on. All right. So the student class will take self. It will take a name and it will section. It will take section. All right. And then we'll say self dot name equal to name. All right. Now you see we have defined this error checking and assignment of the value to name already in the parent class. So why should I do this over here? Why should I do it? I can inherit that thing also. So we'll just erase this and we'll call this init method. We can do that. So what we'll do, we'll say either we can say super. So super just means just one above this. So when I was saying parent, So just one above this. So student has adopted humans, so just go to humans. Otherwise, you can just say the name. So you can say human and you can say, just a minute, say human dot underscore underscore init underscore underscore and pass whatever it requires. It requires self and it requires name. All right, this is done. Now you have to assign this section to a attribute called section. So you say self dot section equal to section. All right, so now what it is doing, you see, when you are calling student, it is actually going in this init method and not this. All right, but inside this init method, you have called the humans init method. So it will go there, it will do whatever this init method is doing and come back. And now this instance will have an attribute called name. All right, it will have an attribute called name. And in the next line, we are creating one more attribute called section and assigning the value of section to that attribute. All right, so there may be other functions or not, doesn't matter. Now to check if this is working or not, you can just see and you can say self dot section. All right, now it is working, you see. So it is inheriting from the super class. So I'm just saying super. So whenever you say super, it will just go one above. But when you give the name of the object, you can go 1, 2, 3, 4, and all the above you can go because we're just giving the name of the object type. All right, and if you say just super, so if you just say super and give parenthesis, so it will just go one above. All right, so this will also work. Okay, when you say super, then I guess why is it not working? I guess self is not required then. Yeah, when you say super, then self is not required. Okay, just leave it. Just write the name. It will make it confusing. Right? It is working, but for your understanding purposes, I am just saying write human and give self. All right. So this is what inheritance is. So it is inheriting the property of other objects and also can define new properties. All right. So there can be other humans called, suppose you can say teacher, and then you can inherit from humans. And then you can again define whatever you want to define for this. And this teacher and this student has no relation. It is just dependent on human. So these two are in the same level, but this is on the above level of these two. Any questions? Any questions?
No.
All right, then we'll move on to what we had decided today. So yeah, so in yesterday's class, I showed you what we have covered till now. I'll just show again for quickly. If you come here, can get the course syllabus. Now, just 1 minute. Yes. So all these things are covered over here. We are just left with these libraries, NumPy, Pandas, and Matplotlib. So I'll just take 2 more classes, not next week, next to next week, and then we'll cover this and we will be completing our syllabus. But I wanted to discuss this algorithmic efficiency because it is an important thing to know. Why it is important? Because you are learning programming. And whenever you code, you are actually implementing some algorithm in Python. And since you are actually implementing some algorithm which you have in your mind, you should know how your algorithm will perform. For example, when we were discussing prime numbers, Ram Prakash used to tell me that you should always write, you should write n by 2 instead of n. So what was n? We are just iterating from 1 to that number, and thus and checking if that number is divisible by n or not. And I was just doing for 1 to n, but he was suggesting we can do 1 to n by 2. But you will see those two programs are actually the same when it performs in worst case analysis. And that is what you will learn when we go on to see algorithmic efficiency. So these things are important. And when you take higher, not higher, classes which need these ideas, then it will be better for you to understand the topics. All right. So I guess some of you may be familiar with the concept of algorithmic efficiency, but I'll start from very basic. All right. So now when we are programming, we are actually um, creating algorithms in our mind. Maybe if you are not writing it down, but in our mind we are creating an algorithm and then we are implementing it in Python. So when you write a code, you're just thinking how to solve that problem. And if you go back to our first class, I told you algorithm is nothing but step-by-step instruction. So those programming lines or codes which you are writing, those are instruction to the computer in Python language. And when you write it in some other language, it will become also, but overall it will be an algorithm. All right. And whenever you write an algorithm, you should know how the algorithm will perform. And over here, I have stated three ways to evaluate the performance of an algorithm. The first way is just to get the time for the running time of that algorithm. So you can just take the starting time and the ending time. And when you take the difference, you will know, yes, this is the time my algorithm is taking to run. And the other way is that you can count the number of operations the algorithm is performing in the worst case, maybe. All right, because you don't know when your algorithm will terminate. So if you have a while loop and you don't know when the algorithm will terminate, so in the worst case, how many operations the algorithm is performing. And you will see that these two ways of getting an idea of the performance of an algorithm have some flaws. Therefore, there is something called computational complexity in terms of O notations and abstract notation. So that tells you how the algorithm is performing when it is defined in terms of the size of the input. So I'll repeat again. This um, performance measure is actually dependent of upon the size of the input. And what it checks how the algorithm performs when the size of the input becomes huge, not large, huge. All right. So, and this is very important measure of algorithmic efficiency. And you will see all the algorithms are actually measured this way, the performance of those algorithms. All right. I just bring water. So we'll go one by one. First, the timer method, then counting of operations, and then we'll see how we can move on to this abstract notation of the order of growth. All right. So first, timing. What we can do? Okay, before this. So before this, I should write some code and will be better. So just I'll take this above. So we have talked about this. There is something called uh, time. So this is a module called time, and through this you can actually measure time. All right. So I'll say import time, and then I'll say st equals to time dot time. What this will do is it will actually take what is the starting time. So for now, I'll not run this because I'll just run the code at once and then the start time and end time will be appropriate. Otherwise, the start time will start and we don't have an end time. All right. So I have some module called start time, and what I'm doing is I'm checking prime numbers. So I'll take the same example. All right. So I'll define a function called prime is prime. It takes a number and it checks if the number is prime or not. So I'll run the algorithm. I'll go from the base number to the highest number which the number has been passed, and I'll see if it is divisible by all those numbers or not. So it takes a number. All right. And I'll say for, so we are assuming the number is positive. If you don't want to assume, you can just say if number, sorry, if number is less than 2, just say false. Right. Now for the loop, I'll say for I in range. So we'll go from 2 till that number. All right. So I'll say number plus 1. Should we go plus 1? I guess we shouldn't. Yeah. And I'll check if number modulus I equal to 0. If this is true, then return false. False. All right. And suppose this has run, then we should return true, because if this has run and this if statement is not true, then the number is actually prime. So we should return true. I guess you have got the logic of this is prime check. Is it all right?
Yes, but maybe if you can use less than or equal to on the first.
Why? We are starting from 2 in for loop.
Maybe you start from 3. Anyway, 2 is
What
also a
happens?
prime.
Yes, yes. I was suggesting so. If 2 is a prime number and someone passes 2, then it will give false, right?
Yes,
If you
but
say
if 1
equal
is,
to 2,
if someone pass 1,
1 is not a prime number. 1 is unique number. It is neither prime nor even.
oh, okay. Okay,
Right.
then fine. Okay.
So I'll see if is even, and I'll pass some numbers. Say I'll say number equals to. So I'm just writing it here. You can take an input from the user, 64, and I'll say num. I'll say print f string, and I'll say num is prime. All right, and I'll say else print the same thing, not prime. All right, and then we'll see if this code is running properly. Acha, is even I'm saying is prime. All right, it is working. So I'll define one more end time. So I'll say end, okay, et equals to time dot time, and I'll say print st minus et. That is it, right? And I'll run the code. Not like this. I'll
So
say
uncomment
cell.
is.
Yeah, thank you. Run all below. Now you go here and you see, okay, et minus st. And I'll say cell, run all below. Okay, I'll just select some cell to be better. Cell, run cell. All right, so this is the time it is taking. It is in seconds. Now I can just have the same algorithm. I'll just split over here. I'll just copy these things. And what I can do is I'll just paste it and I'll say, you don't have to go till 2 numbers. You have to just go to 2 to this plus 1. All right. So we'll go from 2 till number divided by 2. I'll take the integer part and plus 1. This is also correct algorithm. So you see, you can have two things to worry about: if the algorithm is correct or not, and if the algorithm is efficient or not. So both these algorithms, this algorithm for is prime and this algorithm for is prime is correct. It will work correctly. All right. But the performance may be different. All right. Why I'm saying may be different, you will see. The average performance is different, but worst case performance is the same. Why? You will see. All right. So I'll just say run cell, and it is taking some time. You see, because this number is very small, 64, the time doesn't change a lot. It is just approximately the same. All right. We can have one more algorithm for this prime numbers. You see, instead of just dividing by 2, we can take the square root. If the number is divisible till the square root, then it is not prime. Otherwise, it is prime. That is also an algorithm to check prime. If you don't remember, you can go back and see your details in mathematics. All right. So you can just go from 2 to, so I have to import one more thing. I'll say import math, and I'll say math dot sqrt, and I'll round it this one, and I'll just round this. All right. I'll just run the code. What did I do? Just yeah, it's fine. So I'll run this code. Now you see it is taking some amount of time, but this time is giving us some idea that this algorithm is performing better than that algorithm if the instance is huge. Otherwise, these times are very similar to 0.01 second, 0.2 second, and so on. All right, 0.02 seconds and so on. Now, what is the pros and cons of using this type of efficiency check, you can say? So you see, execution time varies between algorithms. So if you have a good algorithm, it will take less amount of time, and if you have bad algorithm, it will take huge amount of time. So yeah, you can do that. It can give you an idea of what is the difference between the algorithms if you have huge instances. For small instances, it doesn't matter a lot. All right. Now you see, execution time varies between implementations. So if you have the same algorithm, but if you're implementing it differently, what do I mean by that? You see, this algorithm, you can have other implementation also. So instead of for loop, you can use while loop, or instead of I, you can have one more assignment. You can just say temporary variable equals to I, and you can divide I by some temporary variable. You can do those things. And when you do that, instead of for loop, maybe you're using while loop, or you're assigning it to some other variable. The same algorithm, when you modify or when you do some other implementation, so the algorithm is same algorithm is working, but some different implementation, the time will vary. So it is not an appropriate way to measure the efficiency of the algorithm, because it is implementation dependent. What is your implementation defines the time it is taking for the algorithm to run. All right. So it is not, so it is actually dependent upon the implementation. Similarly, it is dependent upon the computer. So I am running this in a Mac computer. I guess Macs are faster than Windows. So if you have Windows computer, it may take more time, or depending upon the age. So if you have an older computer, it may uh, take more time. So it is computer dependent. All right. So this is also not a proper thing to do. If you have a efficiency checker and it is dependent upon the computer, how will you know if your algorithm is better than some other person's algorithm? You will not be able to tell. All right. Similarly, execution time is not predictable based on small inputs. So what I was saying, if you give small inputs, this time measurement is not appropriate. It doesn't mean anything when you give very small inputs. All right. So this is not a very good measure to measure the efficiency of an algorithm. Now, you might say that, okay, it is implementation dependent, it is computer dependent. What if we just count the number of operations? So what operations do you want to count? We will count the mathematical operations, plus, minus, subtract, addition, and so on. Comparison operations will count. So for each comparison, we'll count one. For each assignment, we'll say one operation is there. And whenever you are accessing a memory in the memory location, we'll count one operations. And one assumptions we are making, that all these operations are identical. So what do I mean by identical? it will, so it doesn't matter if we are doing this operation or this operation, we will count it as one. So we are not saying that this count as twice as this. So this assumption we are making, we are saying that the complexity of this is same as the complexity of this, is same as the complexity of this, and is same as the complexity of this. That is why we can count all those. So this can be a measure of efficiency of the algorithm. How will we measure? The number of operations the algorithm is taking or doing. That is what the efficiency of that or performance measure of an algorithm is. All right. So yeah, this sounds good. Yeah, in some sense it sounds good, right? It has taken care of this implementation problem. It has taken care of this computer dependent problem, because it doesn't matter if I'm running in a newer computer or an older computer. We are not seeing what time it is taking in absolute sense. We're just counting the number of steps it is doing, or not steps, operations it is doing. Yeah, these operations. So we have to define what operations we are counting. These operations we are counting. All right, and then we'll count the number of operations as a function of the size of the input. So what it means, size of the input. So suppose the comparison is being done and it is dependent upon the size of the input. So suppose you are passing a list and you are checking if a number is present in the list or not. So the loop will run on the each element of the list. Therefore, this count of comparison is dependent on the size of the list. That is why I have written is a function of size of the input. So there are some pros and cons to this way of measuring efficiency as well. So we'll see after a break. All right, we'll meet at 7:01. And if you have any doubt, you can ask me before we start. So we'll meet at 7:01 and then you can ask me
Okay.
questions. Yes, any questions? All right.
No.
So we saw that this is also, I guess, seems a good method for checking the algorithmic efficiency. But you see, there are some pros and cons. So what was the objective? Evaluate different algorithms. So you are actually comparing one algorithm with the other. Count depends on the algorithm. Yeah, so this is good. So if you have an algorithm which has more number of uh, operations than the other, then I guess one algorithm is better than the other. Okay, I'm saying it depends on the algorithm. Mhm. Yeah, yeah. All right. Count depends on implementation. You see, I earlier I was maybe saying that it is independent of implementation, but not. I'm sorry. It is actually dependent on the implementation. How you see? So I'll repeat again. So earlier when I was stating this count, I said that it is we are taking care of this implementation, but we are not. I'll show you what I mean by that. You see, when you come over here and this step temp is equals to I. If you don't do this, then the number of operations in the algorithm change. But the algorithm is same. We are not modifying the algorithm. The algorithm is same. But in this implementation and in this implementation, the number of operations are different, but the algorithm is same. So it is actually dependent on the implementation of the algorithm. All right. So that
Which
is
one
one
has
negative.
higher, sir?
So what higher?
I mean, the number of operations.
So you see, actually, we do not uh, take count as a performance measure. So these are the reasons why we don't take counting of operations as a performance measure. So if you are saying that which
I,
is
if this is this is better, temp is equal to I, and using the temp is better, or using I directly is better.
so you see if this step is not crucial for your algorithm, you can just omit it. So this is a very simple example. You can just omit this. All right, you can just omit this and write I. But you know, so your algorithm may have different implementation. This is one example how the implementation can be different. But there are other. I cannot recall currently, but there can be different implementations of the same algorithm. So your algorithm is same. The steps of instructions are the same. What instruction will you feed for this algorithm? It is just saying take a number, start from 2, and first check if the number is greater than 2 or not. So that is a part of the algorithm. All right. And if not, then start from 2 and increment 1. And each time you take the remainder. If the remainder is 0, then it is not a prime number. If the remainder is not 0 till the end, then it is a prime number. And how will you increment? You will increment from 2 till the number itself, or 1 less the number itself. All right. So this is the algorithm. And how are you implementing? It depends upon what assignments you are doing, how you are defining the data structure. Maybe you are taking some list. You are not doing in a for loop. You are saying that I'll create a list from 2 to till that number, and I'll take each element of the list and then I'll divide it. You can do that, but the algorithm is same, right?
Yes.
So it is up to
Mhm.
you how you're implementing that algorithm. So
Oh,
this is actually dependent on the implementation. It is independent on the computer. So you see, this thing we have taken care of. The number of operations I have in this algorithm will not depend on the computer because we're just counting the number of operations, comparisons, mathematical operations, assignments, and so on. Now, the assumptions we made was these four operations are identical in terms of um, what should I say? Uh, time, or I'm not getting a good term. So these are identical in terms of time it takes maybe. Yeah. So this is the assumption we made because one assignment is same as the mathematical operation we are saying. That is why we are counting this as 1 and also this as 1. So this is one assumption which may not be correct. Yes. Anything, Tanish? All right. So we will see one way of how we count some algorithm. So we will see one example how we are counting the number of operations. All right, just for demonstration purposes. It is not required maybe. So what we'll do is we'll take a number from the user, and what we want the sum of all the numbers starting from 1 till that number. So I want the sum of all positive numbers from 0 or maybe from 1 till that number. All right. So I'll say sum of num. All right. So this is the function name, and I'll pass the number. So I'll say num. Or you can have another function maybe which take the sum of all the elements in an array. You can do that also. All right. So let us do that maybe. It doesn't matter. Sum of elements. ELEMENTS. Right. And I'll take a array. Now we'll say total equals to 0, and I'll run a loop for I in ARR. What do I want to do? I want to do total equals to total plus I. All right. Now I'll say return total. So this is a very simple algorithm to get the element wise addition or element wise sum of a list. All right. I'll just not call this function. We'll just see how we're counting the operation. So we'll say this is one operation. One operation. Over here, this loop will run how many number of times? It will run LENARR. All right, so it is dependent on the size of the input. Now, how many operations are we making? You see, when we are taking individual elements from the list, this is also an operation of this type, accessing objects in memory. And we are saying we'll count it as one. So we'll say one operation each. So one ops each iteration. All right. Now over here, we are actually doing two operations. First, we are actually adding two numbers and then we are assigning. So we'll say two operations per iteration. Per iteration. Okay. And this return one iteration. We are saying so. This is the difficulty. How which will you say one iteration and which will you not say one iteration? For now, we are saying return is also one iteration, or not one iteration, one operation. All right. So how many operations are we doing? You see, if suppose the length of this is n, so you are doing 1 plus 1, 2. So I just write over here 2 plus. So this will run n number of times. So 3n. So 2 plus 3n is the number of operations this function is taking. All right. Is it all right? 2 plus 3n. Now suppose the same function, I did a different implementation. I said I'll assign first I to temp, and then what I'll do, I'll add instead of I'll add temp. Over here, you see this is one more operation per iteration. Per iteration. Now, what is the change in complexity? You can say you see it was 2 plus 3n. Now it has become 2 plus 4n. All right. So this is dependent upon the implementation of the algorithm. So this is not a good way to actually measure the efficiency of algorithm or complexity of an algorithm. All right. Now, can we do better? You see, counting of operations was somewhat better than taking the time. All right. Sorry, taking the time of implementation of the algorithm. So what I have written, focus on counting operations, emphasis counting operation in algorithm, ignore minor implementation variation. Yeah. So what will we do is, you see, there are three cons to this algorithm. First, we don't know which operations to count. All right. We don't know if this operation, return operation, is taking more computational power than addition or subtraction or assignment. All right, but this way of measuring was dependent on the input size. So you see, we have n over here. So this is good. If the input size increases, the computational complexity of this will increase. We know that. We already know that. So it is actually dependent on the input size. All right. Moreover, decision on what measure to take, decide what to measure, consider factors that may such specific trial details. What did I mean by this? I forgot. All right, so yeah, we'll move on. So we will see. You see, when we implemented this algorithm over here, we had a for loop from 2 to number and one more for loop from 2 to number by 2. And from common sense, one can say, obviously, this algorithm is better than this algorithm, right? Obviously, but it will be better in the average case. So when you will say average case, then only it will be better, not in the worst case. What do I mean by worst case? What do I mean by average case? We will see. So consider this example. Suppose what I'm doing is I'm taking a list and I'm taking an element, and what I'm doing, I'm checking if this element is present in the list or not. This is one function. So what I'm doing, I'm taking individual elements from this list and then I'm comparing. If I equal to E, then return true, otherwise return false. So what will be the best case? The best case will be that element is present in the first index of the list. If that is the case, it will take minimum runtime and the algorithm is constant. So what do I mean by constant? So you see, it is just taking one operation. In the best case, it will just take one operation. That is what I meant by constant. All right. In the best case. All right. What will be the worst case? The worst case will be the element is present in the last index of the list. And then this operation will run linearly in the size of list. So if the size of the list is n, the number of operations it will take is n. So in the worst case, it will take n operations. Now in the average case, you see, any possible value can happen, but in the average case, it will actually take half the size of the list. So if the list is of n size, it will actually take n by 2. But when n is huge, by huge I mean huge, because you see, in today's time, data is everything. Everything is data. And when you have millions and millions of data you are feeding to something, so n by 2 and n doesn't matter. So in this kind of measure, which we will see order of growth, we only consider worst case performance of algorithm. Moreover, these constants. So if you say 2n operations and n operations, we will say 2n operations and n operations will perform the same in the worst case. Because if n is huge, billions of in size, then twice of n and n in the worst case is same. This is what how order of growth is measured. All right. So this is the idea. Always measure the worst case performance of the algorithm and consider the input size to be huge. And whatever the measure you get, we denote it by capital O. So this way we denote it by capital O, and inside the bracket, we will give a function of the input size. And what it measures the worst case performance of the algorithm when the input size is huge. So it measures, so I've written here, it actually gets a upper limit on the asymptotic growth. So if you know what asymptote is, it is a mathematical term and it means when the not input. So I'll just show you what asymptote is. So it is approaching infinity. If you tell in English, asymptote is approaching infinity. TOTE, asymptote. So what it says is, you see, suppose we have a curve and this line will touch this curve asymptotically. it means that this line will touch the curve at infinity. So this is a mathematical term, but this is what it means. So when we say asymptotic growth, it means that the input size is infinite, not infinity. You cannot say it is infinity. It approaches infinity. All right. So where were we? We are here. Yeah. So this is how we measure the performance of an algorithm, and it is denoted by capital O. And inside the bracket or parenthesis, you write what is the complexity of the algorithm. All right. So we'll take an example of factorization. You see, we have two implementation of factorization. In the first implementation, what have I done? I have taken the input n, and so whatever we did earlier. So over there we were checking a prime number. Over here we are just not doing factorization. Sorry, factorial calculation. I'm sorry. This is factorial calculation. So we are taking 1 and we are checking if n is greater than 1 or not. So and then the earlier answer was 1 and we were multiplying n times answer and we are decrementing n by 1. So in this implementation, we are doing this, but in the second implementation, we are assigning n minus 1 to a temporary variable and then we are saying n is equals to temporary. These two are the same same algorithm, but different implementation. Over here, I'm using a temporary variable. Over here, I'm not using a temporary variable. Now, if you count the number of operations or the number of steps it is taking, the second algorithm is actually taking more number of operations than the first algorithm. All right. The second algorithm will take more time if you see time taken for this algorithm to run. But in the worst case, in the asymptotic case, these two algorithms will perform similarly. See, why? Because you see, how many loops we will run? We will run n number of loops. All right. So this algorithm over here, this part runs in n operations. So if you just count by operation, this will not operation iteration. Sorry, this will take n iterations, and n is dependent on the size of the input. So if n is large, so if you say if you pass 4, it will take 4 iterations. If you pass 1000, it will take 1000 operations. So the number of operations or iterations, sorry, I'm confusing you. So number of iterations is dependent on the size of the input. And this also will take n operations or n iterations. And when n becomes huge, number of iterations over here and number of iterations over here, although same, here we are doing more operations, but when n becomes huge, these small operations will not matter because these are constant time operation. It will just assign the value to the temporary variable. It only depends on the size of the input. In the worst case analysis, when n is huge, both these algorithms perform the same. Both these implementation of the algorithm are identical. So if you say order of growth notation in O notations, this is also an order n algorithm. This is also an order n algorithm. Actually, those both are same algorithm. All right. Now, what have I written? Ignore additive constant, ignore multiplicative constant. So over here you see, so I'll just break it down for better understanding. I'll run this. Yeah. You see this algorithm. I'll say number 1. How many operations we are doing? We are doing one operation over here. This is one operation per iteration. This is 2 operation per iteration. Why 2? First the multiplication and then assignment. So we had 1 for this plus n times loop will run. Now this line will actually take 2n operations. Why? Because multiplication is 1 time and assignment is 1 time. So this line will take 2n operations. All right. This will also take 2n operations. Why? Because first we'll subtract. So the subtraction operation and then assignment operation. So this will be 2n operation. And then this return is just, I'll say 1 operation. All right. We'll say plus 1. Now for the second algorithm, All these are same, just one assignment is this line is there. So this is also two operations. N minus 1 is one operation, and then assignment is one operation. So there will be plus 2n. All right. So what is this? This is equals to 2 plus 5n. 2 plus 5n. And this is 2 plus 7n. All right. So these are the number of operations for the first algorithm, and these are the number of operations for the second algorithm. So what do we do when we calculate the order of order of growth? So we will ignore the additive constants. So these are constants. You see 2 is a constant. It is not multiplied by n. So we'll ignore the additive constants, and we'll also ignore the multiplicative constants. We'll ignore these constants. All right. Therefore, we'll say it is actually order n. So it only grows with the size of the input linearly. This algorithm, first algorithm. So second algorithm also will ignore this part and also this part, and we'll say order n. It is growing linearly with the input size. All right. So I have written what does n order n measures. So you can just read it. I have explained to you what it means. Now there can be different. So I have given some examples. So you see there can be an example like this. So what does it mean? We just divide again and just separate this part. Run this and run this. So I'll give one example of this. All right. So you see I have a for loop for I in range, and suppose there is some input n. I'm not doing that. So suppose we are inside a function and this n is the size of the input. And inside this I have another for loop for I in range n. All right. Suppose there is some matrix or something like that. And we are printing. So print I comma j, something like that. And inside this, so let me define a function for better clarity. Def test n. So this is one part, but there is one more for loop doing something else. So I'll say for I in range n. And what does it do? It does something, say I equals to print I. All right. And then some return statement is there. All right. Return I. Doesn't matter. Or return true. So you see in this algorithm, the first for loop runs n times, and for each I, the inside for loop will run. So these two for loops actually runs n square number of times. So this is what it is written n square. Over here, it is running 2n number of times. So I'm just saying this is running n number of times, and suppose some operation is there and it is running 2n number of times. And there are two constant operations. So one is in the return statement, and suppose there is some assignment I equals to 0, something like that. So this was the number of operations the algorithm was taking. But when you say order of complexity, we will say it takes order n square operations. Similarly, for this example, you see, although these numbers are huge, these are huge numbers. This is actually 1 lakh over here, and this is 31,000. But still, we will say we'll just ignore these constants. You may argue that, yeah, this is very huge. How can we ignore these numbers? But think of it like this. If n is billion, so if n is billion, n square will be such a huge number. So, and we are measuring asymptotic behavior. All right. In that case, these numbers will not matter. And now you may ask, if this is n square and this is n, then why are we ignoring n? We can say order n square plus n, but no, this n square will dominate this term. N square will dominate this term. So we'll ignore everything, this part, and just will say order n square. Similarly, if you have this operation log n plus 4, log n is actually smaller than n. If you don't know, you can check. Log n is actually smaller, actually quite a bit smaller than n. When n is large, then it becomes order n. So whichever is the dominating term, will take that term. In this case, You see, you may argue that this is very small and this is also very small, and when we're multiplying by n, this term will become very small. But remember, we are only worried about the worst case performance. Therefore, we'll not take this term. We'll take only this term, and which is dependent upon the input. So this is dependent upon the input n log n. So the complexity will be order n log n. Similarly, for this, you may argue, okay, this is not correct actually. This is like this. All right. So over here, you may argue that n to the power 30 will be larger than 3 to the power n when n is small. But always remember, this is worst case performance. N is huge and exponentials are always bad. You see, I have given a graph. So this is constant operation graph when this n is the input size. So x-axis is the input size, and this is the computational complexity. So for constants, actually this will, you can draw this anywhere, but it will remain constant whatever be the size of n. This is logarithmic scale, this is linear scale, this is log linear, so n log n. This is quadratic, other polynomials will be here. This is exponential, so 3 to the power n, 2 to the power n, it will come over here. And factorials are worst. If you have some algorithm which is in factorial complexity, it is the worst of all. It grows more than exponentially. So exponentially is bad, not bad. Exponentially is also very, very bad. And if you have an algorithm which runs in factorial, then it is, you don't have anything. You can say you don't have an algorithm to solve the problem. All right. And when you learn about these topics more, then you will see there are something called NP hard problems. All right. So, and there are classes of problems. So I'll just show you. It is in very interesting topic, a bit mathematical, but very, very interesting topic. And there is a one YouTube video which I saw, which was very good. I'll just show you the link of that YouTube video as well. Complexity classes. You see, these are complexity classes. All right, I'll just show you a simple one. So whenever you have P, it means polynomial time. So these algorithms runs in polynomial time. All right. So order n square and so on, and all below. So order log n will come in polynomial time, because if it is polynomial, so if it is running in polynomial time or less, then it will be in polynomial time. So constant algorithms, log algorithms, log linear algorithms, and other polynomial algorithms will be in this polynomial time section. Then there are non-polynomial time algorithms. Okay. I don't know these topics. These topics are huge topics. All right. Yeah, this is a better diagram. Yeah. So there are something called NP complete problems. Those are very difficult problems, you know. So this is not very good way to tell you, because I am also not a very good person to talk about this. I don't have experience on this, but if I get time, I'll read about this sometime. All right. And if you're interested, you can see one video. I'll share the link of that video in the WhatsApp group about these classes. And this is a very good video for some novice person who don't know about complexity classes. I'll share that video with you. All right, so we have seen this. Now what is left? Analyzing. Yeah, so I have shown you how can you analyze some uh, algorithms using this order of growth notations. So I have given one example over here. You see, suppose this is your algorithm. This is what your algorithm is. There are no other steps. So there is one loop I from range n, and another loop j which ranges from 1 to n times n, or 0 to 1 n times n. So what is the order? You see, the first loop runs is in order n time, order n operations, or order n complexity is for the first loop. The second loop is actually order n square. Why? Because that is the number of times the loop is running, and therefore the overall complexity of the algorithm becomes order n square. Similarly, so this was one example of addition. There is one more example of multiplication, which I'll show you, and which we have discussed actually. So this loop is running order n times, and this loop is running order n times. And for each iteration, this loop is running n times. So you can say this is order n, this loop, this is order n, and when you multiply, it becomes order n square. So this is the size of the algorithm, computational complexity of the algorithm. Now, this is the order of so if you have some algorithm in the initial few lines, then those are good algorithms. As you go down, your algorithms computational complexity becomes bad. So as you can see from this graph, so constant time algorithms are better than logarithmic time algorithm, which is better than polynomial time algorithm, which is better than n log n algorithms. Okay, this is not polynomial, this is linear. That is why I was thinking. And which is better than polynomial time algorithm, which is better than exponential. And I have not written over here this factorial, all right. So over here, I have given some examples of constant time algorithm, logarithmic time algorithm, linear time algorithm, and polynomial time algorithm. All right. So we'll just go through this one by one. But before that, any questions?
No, sir. Nothing.
So are you able to understand?
Uh, Sir, how that logarithmic time will come, sir? Linear time, okay, fine.
Logarithmic time. So binary search is actually log n. Computational complexity of binary search is log n. Binary search time complexity. Yeah, binary search is log n. So what it happens, I'll just tell briefly. You see, we had discussed binary search in initial first class, our first class. I had not taken this term binary search, but what it does, you see, if you have a problem size of n, what we do, we divide the problem in between. So I'll just this is not binary. Okay. Yeah. So you see, you have 1, 2, 3, 4, 5, 6, 7. Now what you are doing, 7 is the size, you're breaking in between. So we had taken an example of dictionary. We said we will open the dictionary in between. All right. So at each iteration, your problem is becoming half. So initially you had n, the size of the problem was n. In the next iteration, it becomes n by 2. In the next iteration, it will become n by 4. All right. So I'll write over here. First, it is n, then it becomes n by 2, then it becomes n by 2 to the power 2, that is 4, then it becomes n by 8, then it becomes n by 16, and so on. Till when? Till the time this number or this number becomes 1. So it will become dot 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 till 1. All right. Until it becomes 1, we will run it. Is this clear? Is this clear? This is how binary search works. So if you are talking about a dictionary, you will open in between and you will ask a question, whether to go left or whether to go right of the dictionary. You will pick one. And when you pick one, your problem size has reduced to half of what was before the that operation. Now again, you will go in between, in middle, and you will ask whether to go left or whether to go right. And then your problem has reduced to another half. Is it clear? So till when? Till we have only one page left. So is this clear? N by 2, n by 4, n by 8, and so on till 1. So you see how many operations are we performing? So you see we are doing. So I'll just use some LaTeX code. If you don't know LaTeX code, just give me one time. I'll just, so it will be frac 2 by n to the power p. Just let me write it first. Equal to 1. So what does this mean? Okay, this is very small. I hope you can see it. What I am doing is I am saying so So the loop is running p number of times. I guess it is very small. Can I increase this size? Just open overleaf maybe. It will take some time. Okay, I hope this you can see this. So you see what I am saying. So you have to respond, by the way. I will not understand if it is clear. Huh? So is this clear? N by 2, n by 4 till 1. Is this clear?
Yes, sir. So divide and conquer method will go for this only. N by 2, n by 4 like that.
Yes. Now what I'm saying is I am running the loop n number of times. So suppose this loop, not n number of times, p number of times. We don't know p yet. We want to find out p. So we are saying that this loop is running p number of times. All right. Now, when this becomes 1, when will it become 1? You see, you're dividing 2 first by n, it becomes n by 2. Again, if you divide 2 by n square, it becomes this. So I'm saying when you run p number of times, this thing, it becomes 1. So is this clear? 2 by n to the power p equals to 1. Is this clear? 2 by n to the power p
Okay,
equals to
sir.
1. Is this clear? So I'm saying if you run p number of times, the size of the problem becomes 1. So how are we running p number of times? At each iteration, I am dividing. Okay, I am saying n. Sorry. You should tell me. I'm doing it wrong. It is n by 2 to the power p equals to 1. Sorry. So at each iteration, I'm dividing n by 2. And how many times we're dividing n by 2? P number of times. Now I have written it correctly. N by 2, n by 2, n by 2, and it will go till it becomes 1. So is this clear? N by 2 to the power p equals to 1. Hello. Are you there?
Yes, sir.
Yes, thank you. Now, if you want to find out what p is, so I'll just take one more code block. And if you want to find out what p is, you have to use this log formula, by the way. If you don't, I'll just show you. Log to power. It is not actually a formula. It uses simple logarithmic rules, but I'll not go there. You see, if you have b to the power a, which is equals to n, how can you change it to log? It will become log, and this b will come to the base. This n will become what the factor is, and which it will equal to a. A is the power. All right. So this is what we'll do. So over here it becomes n equals to. So I'll just write some LaTeX code. Maybe it is better. So I'll just say n equal to 2 to the power p. Right. So this is what it becomes. N is equals to 2 to the power b p. Now you see, if you take log of this, because you want to find out what p is, that is what we are worried about now. What p is. We're worried about what p is. So if you take the log of this, then p becomes p equals to log to the base 2, and it will be n. I hope I have written, yeah. So p equals to log to the base 2 n. If you change it, so you see this formula. This b will be the base of log. What is b here? 2. 2 is there, so 2 will be the base of log. All right. So it will be log 2. Whatever is in the power will come to equal to. So what is in the power? P is in the power. So P will be at the equal to side. And whatever is there in the power of B, no, whatever is in the equal to sign will come to log. So what was in the equal to sign? N. So it comes to log. All right. And this is not some formula. It is very simple logarithmic rule. And if you want me to tell you, I'll just tell you maybe. So you see, we'll take log on both sides. So I'll say log of n equal to log of 2 to the power p. To the power p. All right. Now anything to the power p, you can take that power in the um, beginning of log. So it will become actually log n equals to p log 2. All right. So it will become this. Now what we do is we take this log 2 over here, we divide it. So we'll say log of n by log of 2. So in LaTeX, it is written like this, FRAC. When it compiles, then you will be able to understand what I have written. Log of 2, right? Which is equals to p. Let me compile it. So you see, these are the steps. Over here, you take log on both sides. So log n is equals to log 2 to the power p. Then this p will come over here. So it will become log n equals to p log 2. Now we'll divide log n by log 2. So it will be log n by log 2 is equals to p. And there is one formula of this logarithms. If you have log a by log b, it becomes log a to the base b. So it is what it is. Log n to the base 2. All right. So these are the steps of converting a power to a log and log to a power. All right. So yeah, what I was telling is, so you see what is p? P is the number of iterations for this search, divide and conquer or binary search, whatever you say. And what is p? P is actually log n. And this is actually the complexity of that algorithm. Log n, order log n. Yes, you can speak. Any questions?
No, sir, nothing, sir. Clear.
Okay, thank you. So I have written some examples of constant time algorithm. It is nothing, just printing some code. If you run that algorithm, it just prints. So it is constant time. It is not dependent upon the input size because there is no input over here. You may have some input, but it just prints. So it will be constant time algorithm. Therefore, it will be order 1. All right. Now I have written a logarithmic algorithm. So this is what binary search is. I have written the binary search. You can go through, and in the assignment 2, you have done a binary search. Not 1, 2 questions are there on binary search. So I don't need to explain, I hope. Then you can go through the binary search, and this is how it is calculated. The complexity of binary search is log n, and it is a very good search algorithm, by the way. All right. Some linear time algorithm is just a loop. If you have one loop and the loop is actually on the input, then it becomes order n, where n is the size of the input. All right. This is also linear time algorithm. It is actually adding the elements of the list, which I had shown you earlier. So this is what it is doing. This is also a binary, sorry, not binary, linear time algorithm. Why? Because you see what it is doing, it is actually calculating a factorial. So you see this loop is actually running from 1 to the number itself. And there is no other loop there which is dependent on, or no other operations there which is dependent on the size of the input. Therefore, it becomes order n algorithm, which is a linear time algorithm. This is a polynomial time algorithm, actually quadratic. There are two loops, one inside the other, and therefore it is order n square complexity. All right. So generally, if you have nested loops, those are polynomial time algorithm. Generally, not always, but generally. All right. This is also a quadratic time algorithm, which is order n square. What it is doing is it has two lists, L1 and L2, and I want to see if L1 and L2 are the same. So how will we do? We are taking one element of L1 and comparing it with all the elements of L2. So it is not order n square, it will be order n. So where n is the size of L1 and m is the size of L2. You shouldn't say order n square. Huh? If I had said that, it is wrong. It is order mn. M and n both may be different, maybe same, but maybe different. So how it is doing? It is taking individual elements of L1 and comparing it with all the elements of L2. Then it is taking second element of L1 and comparing it with all the elements of L2, and so on. So if the size of L1 is n and the size of L1 is m, then it is order mn. All right, this is it. Or so this is not. So these are just, we are scratching very minute part of this topic. This is a huge topic. All right. Any questions?
Hi, ma'am.
Sir, like a big O notation, we also have big theta, big omega and all, right?
I am not aware of that. I have
Uh,
to see, I
Actually, I
guess.
have one small doubt in that. Okay, sir, leave it, no problem. When this big O will come, when will big theta will come? Because I'm also working on algorithms. I We also proposed algorithm with big O itself, but should know. I need to know the idea. No issues, sir. Problem.
All right. Any questions? So yeah, any questions?
No, sir, nothing from me, sir.
All right. So I'll share the video link. All right. Acha, by the way, I wanted to show you this graph. Yeah, so this is the lecture notes of MIT. So it is showing the size of how the input size increases. So if you have algorithm of complexity order 1, then order log n, then order n log n, order n square, and order 2 to the power n. All right, so n is here. So first n is 10, then n is 100, n is 1000, and this is just square of 1000, 1 million. All right. So you see the size when it is order 1. So it is 1, 1, 1, 1. So these are the uh, values of that n, you can say. So this order size. If you have log n, it just counts the number of zeros. So this is 1 0, this is 2 0, this is 3 0, this is 6 0, and so on. So only 6 iterations will be required for this kind of algorithms. If you have a size input size of 1,000,000, this kind of algorithms will only take 6 iterations. Order n when the base is 10, by the way. So over here the base is 10, not 2. In binary search the base is 2. But no matter what the base is, if you have log of something, the complexity is written as log, right? So the base of this is 10. Now if you have order n, this will take 10 iterations, this will take 100, 1000, million. If you have n log n, this is the how it increases. If you have n square, this is how it increases. And if you have order 2 to the power n, you cannot imagine what this size will be. By the way, you can print this in Python. I don't know if this my computer will freeze, but let us do it. 2 to the power 1 million, 1, 2, 3, 4, 5, 6. Wish me luck. Okay, power, sorry. I don't know what will happen. All right, let it run. So can you hear me? My computer has not frozen, right? You can hear me.
Yes, sir, I can hear you.
So let it run. It will take some time. I want to show you that program and the hard computational complexity. This video, very high quality video, right? I'll just share in the WhatsApp group. If you have time, do watch this video. Right, okay, it has printed. You can see what is the size. Don't run in your computer, by the way, it may take a lot of time. So my computer has froze. There are more numbers, by the way. This is not blank. There are more numbers. Okay, so you have the idea. There are more numbers, but my computer is not able to show it. I just delete this part. Okay, it is not be able to delete also. All right, so yeah. So you see next class, will actually be on 7th, I guess. No, 9th, 9th of December, right? And we'll have only 2 more classes, 9th and 10th. And the project assignment submission date is 8th of December. So anything on that?
No, sir.
All right. And Danish, how do you want to cover up all the lectures if you want to submit the project? I don't know. All right. So I'll just mark the attendance.
So for how long the recordings will be available after the class?
For now, I'm not planning to delete the recordings. So yeah, maybe 3-4 months it will be there.
Okay, sir.
All right. 4 participants, right? 1, 2, 3, 4. Yes. 4 participants. Yes. Thank you.
Thank you, sir.
Ending the. Yeah.
Thank you, sir. Thank you, sir.
So one last thing. Oh, okay, ma'am has left. All right.